Hi, everyone. Welcome. We'll get started in a couple minutes. Okay, it's 12:30, so let's get started. Thank you so much, everyone, for coming today to QuantSim. A special thank you to Roy for presenting. And Roy requested a short introduction. That is that Roy went to a bunch of schools, received a bunch of degrees, and has worked at NIMS longer than anyone cares to remember, and is now working at the Environmental Research Division, formerly PFEG, of the Southwest Fisheries Science Center in San Diego, California. Roy will take questions as we go as much as possible. So thanks again, everyone, for coming. And with that, it is my pleasure to turn it over to Roy. And I'll just mention, we were unfortunately unable to get Roy's video working, but yeah, we look forward to hearing you speak about your work.
Okay, can you see my screen?
Yes.
Okay. Anyway, thank you. So yeah, I'll take questions as we go. If I feel that it's going to tie up the talk too much, I'll put it to the end, or if the discussion goes too long, I'll put it to the end, but I'll stay as long as possible afterwards if people really have questions, so that I'm also very good at blowing off questions. So if anything's too hard, I'll find a way just to blow you off so I don't have to answer it. Okay, I actually made this slide about a month ago, but it has more meaning this week. I mean, I didn't want the machine learning guys, the only guys that have fancy names for their thing, you know, so this is getting, but what makes it relevant is if you know anything about Wagner and his beliefs and why he didn't like Mendelssohn, given that we've had people in the Capitol with sweatshirts saying 6NWE, it couldn't be more appropriate. You might, if you don't know what that stands for, you might look it up. I don't know that I have that much useful, and I always want people to get one useful thing out of the talk. So if you don't know about it, it's called Dutch door opening. You should learn to not open your door with your closest hand to the door, but with your far hand, because that makes your body turn so you see bicyclists approaching. So that's a good advice. And so now you've learned one thing, so you can go to sleep, because I don't know how useful the rest of the talk will be. Okay, I've been involved in working with data that's dependent in time, and some of the issues, and in space, and some of the issues when data is dependent in time is situations like this, where you have a mean jump in the data, or situations like this where clearly the variance in the data is changing. As you see, you have very little variance here and a lot of variance there. Or situations like this where we have the series much below the mean, and then it reverts to above the mean, so we have a change point right there. Except, does anybody know what the except is? If you've heard my talks before, you're not allowed to answer. Any guesses on what the except is? No guesses? Okay, well, the except is everything I just told you isn't true. This is a stationary series. Stationary series by definition have constant mean, constant variance, constant log variance structure. So you've probably seen a lot of papers with stuff like this. There's no change in the mean here. It's stationary. Same thing with this. This is a stationary series, Howler's generated. There's no change in the variance. And same thing with this. This is what you've seen. If you've seen a lot of the papers on the quote 76 event, you'll see that the series started warming or changing around 72. It stops changing in 84. And this is what the point that's being said to be a change point. That doesn't look like a change point to me. And the point of this is that time series that have dependence can have a lot of transient behavior and complicated transient behavior, and modeling that properly can be very difficult. Real series have very complex dynamics, very rich dynamics. For example, Darwin pressures have a trend, a non-parametric trend like that, and a stochastic cycle that changes. So it's not a fixed cycle, but it's a cycle of changing phase and amplitude. And here's a seasonal component of wind stress curl, and you can see it's changing dramatically over time. And so we're going to deal with temporal dynamics of data in the ocean. We have to have methods that allow us to have a very rich temporal dynamic. We can see this again if you did the old style way of doing the state space with Kalman filter. The filtered state is predicted time the gain. The gain is approximately the process noise over the measurement noise. So this last term is roughly the new information in the data point. And what it shows is that if we have a highly correlated process, the new information in the data point is very, very small. And if we have an error one process for Bartlett's correction, if we don't correct for the autocorrelation in the series, the actual variance is probably 4 times bigger than what we're seeing as the variance in the series. Spatial data problem adds even more problems. Here's a paper that showed that if he took two randomly generated spatial fields and he did the correlation, you can see he gets a nice fit on the data, even though they're independent. Another paper showing that predictors, you get a lot of overfitting and a lot of inflation of the results. Even more, a lot of people saying, well, we did cross validation, but cross validation's also been shown when there's spatial and temporal. Cross validation especially assumes independence in the data. I mean, it's a little more complicated than that, but cross validation also gives inflated results when there's spatial and or temporal correlation. Spatial data adds even more problems. I want to focus in on this part where there's upwelling. And one thing to think about is the upwelling behavior, particularly like in here, is really different than the behavior in the other areas. And think about it if I have a method where everything is with equal variance. For example, if I have a correlation matrix, if I standardize the data, the areas not in the upwelling are much, much more numerous than the areas in the upwelling, and they will overwhelm the analysis if the amount of variance is our criteria. For example, if we're doing something like EOFs, and also in determining the spatial scale, we look at if our spatial scale is 5 degrees, like say in the PDO, the upwelling area is going to get wiped out. Also, just as a note, you should never use the kind of colors I just showed you because the color change is deceiving. You think there's a bigger change than there is. Changes between color look bigger than changes within color, even though the same size. You should use well-formed color bars, something like this. This is from the CM Ocean color. This is an example of chlorophyll. One, we can see how highly skewed the chlorophyll distribution is. We can also see that the spatial scale of chlorophyll near the coast is very different than the spatial scale away from the coast. So even if we do a spatial correction, and our spatial correction is homogeneous, so we're assuming a same spatial scale throughout the data, that's not going to fit very well because this is where the main chlorophyll concentrations happen. And again, this is going to have a very different spatial scale than here. Also, nice thing about chlorophyll, I worked with a South Korean scientist, and she had a study where they were looking to predict HABs from using chlorophyll. And besides having satellite data, they also had a series of shore stations all along the area she was looking at that was measuring HABs. And what she found is if you looked at the areas where there were significant HABs, there was a pretty good relationship between chlorophyll and HABs. But if you looked at all the areas, it broke down. And that's because there were a lot of areas that had chlorophyll, high chlorophyll, that didn't have HABs. And that's selection, what's called in a lot of the selection bias. And it's a very serious problem in some of the work. So it's something you have to be very careful of. And again, you should never use the kind of font color bar I just showed you in a real paper because it gives misleading results. You should use something like from CM Ocean that gives single color with different shades. Again, this is looking at SST gradients and frontal, if you want to measure frontal structure. And what you get a lot is people, for example, have tagged animals, and they'll say the tagged animals found along this frontal structure, and fronts like this might last 3 to 5 days. You could get several hundred, 7,000, several thousand, who knows, observations. If it's used by a method that assumes independence, which a lot of machine learning methods do, it'll view, wow, this is really strong. Look at all the observations we have along the front. But now what happens, people often treat the what was estimated, which was conditional in both the environment and the animal being there, they treat that as the same as the unconditional, where we're not conditional environment. And if you think about it, it will then say that the animal was likely to be in all of these regions with a strong front. And that prediction will be very, very misleading, probably extremely, extremely weak. Okay, and so before we get on this, in summary, if we don't properly account for the data generation method in how we analyze the data, we can get really misleading results. And we can see that, for example, there are a lot of, like in IEAs, now these supposedly indices series, if you look at a lot of those, you'll find that they're stationary, and yet they're fit with a 5-year trend, fit by ordinary least squares, even though there is no trend. You have statements like the PDO predicts Pacific productivity or salmon. I would say that if it predicts it at all, it's probably only very, very noisy. And I'm saying if you want to get away from this area, species distribution model techniques were used in last April in looking at the spread of COVID-19. And if you look at that paper, let's say the results were really, really far off. And again, for the same reason, selection bias and confounders not being properly considered. Okay, getting more onto the top of this paper. This is from a paper I did many, many years ago. I looked at tuna along the Gulf of Guinea, and the long and short of it, it seemed to suggest at certain frequencies that the sea surface temperatures sort of propagated along the coast, and that the tuna followed behind it with a slight lag. And I was asked to look at tuna in the Eastern Pacific, and I wanted to update the data, the methods I use, because this was done very, very long time ago. Um, to see some idea that there really is a phase lag in some of the series. Here's temperature data from an estimated of the seasonal component, where each location was done with a state space decomposition. And if we look, it does look like there's the same behavior among the locations, but with a lag in the behavior. So basically it's saying that there's really only one thing going on here, but the one thing has a lag. So the question is, how can we model that? And so now my little joke, I'm a bit worried about Mike's obsession with the difference between sine and cosine, and don't worry, it's just a phase. And if I don't know how much how much they teach frequency domain stuff these days, but that's my joke. So anyway, the first method is a frequency domain method. It's quite old. Basically, almost everything I'm talking about here can be found in Brillinger's old book on time series. And what we're going to do is take the Hilbert transform of the data, and that gives you basically a quick estimate of the phase and amplitude of the series. You can again see that in Brillinger. If we look at the state space way of doing a cycle, including doing the trigonometric thing of the seasonal, it basically does the same thing. It has the series and its Hilbert transform, and you can derive that using the identities to rewrite it that way. So there's a relationship between the Hilbert transform and how state space methods do frequency, a component, with a cyclic component that has changing phase and changing cycle, changing amplitude. So what we can do is take the Hilbert transform of the data, and then we can do the usual EOF type calculations, except for complex valued series. We can calculate the amplitudes in the real part and the phases from that. Okay. So problems with doing this is it assumes stationarity of the data. It shifts all frequencies at once. So that means it only makes sense over limited bandwidth. So we have to have some way of filtering the series. You can't have missing data. You're implicitly estimating a ton of parameters. When you all such methods, that are looking at eigenvalues and eigenvectors of a matrix have tons of implicit parameters, and our estimates are global in space and time. So there's no regularization in time to make it smoother, to filter out noise, and there's no smoothing in space. So there's nothing forcing neighboring areas to have similar behavior. And like in the upper link case, I showed local dynamics can be overwhelmed in the analysis. Having said that, it could also give us a rough idea whether it does look like there's phase lag in the series, and therefore it's worth looking at. Again, there is a degree of freedom in the analysis, in that where I put 0 phase is totally arbitrary. And therefore, when we look at some results in this thing, I don't know how much people are familiar with frequency domain methods, but when you look at what color is shown, if I put 0 phase here, these are viewed as coming later, these are viewed as coming earlier, and these guys are viewed as far apart. But if I then shift, the colors change, and things are now seen closer. And if I shift again to down here, these are now closer and these are further apart, because we're mapping, when you do phases, you're mapping to the circle. So you have to be careful when you look at the graphs, because the 0 phase is totally arbitrary. So you can have, like I'm saying, these are actually closer in time than can be seen, but they'll be viewed as further away because of that aspect. Okay, so this is what we do if we look at SST over the region that I'll be looking at Tuna. As you would expect in the first one, there's a difference between north and south of the equator. That's what I would expect. But there is a phase lag in the data. This is for the first component. I mean, this is for chlorophyll, I'm sorry. But if we look at the second component, what's really interesting is we've gotten rid of the difference due to being north and south of the equator, where there's a lag. Would you expect there's a lag in seasonality, and we're getting very, very similar behavior in the areas both north and south, and we're seeing a very clear phase lag pattern in the data. And this is with SST, and again, the first component shows, as we would expect, a north and south difference. But the second component, again, that difference goes away, and we see there's a strong phase lag in the data, and we can see that the phasing is changing through space and time, which is what we would, means that to model the data properly, we have to be able to account for that. SST from this data set has a cycle, not just a seasonal. And here's what the cycle component looks like. It very much is the signature of an El Nino type series. I have a paper that suggests that El Ninos are basically stationary cycles, and we can see the strong phase lag in the data. And this is if we look at the Hadley SST, but this is in 1 degree. It's the same area used in the PDO, but this is a 1 degree rather than 5 degree, and we see the same behavior. But there's a strong phase lag in the seasonal and cycles in the data. Okay, we can also extend it to two sets of series where we use one variable to predict the other. It's just the frequency domain equivalent of the canonical correlation. Brillinger, usually what you see when you do canonical correlations, you have a canonical series for the one variable, canonical series for the other, and the weights, Brillinger shows that there's a symmetric thing where there's really only one underlying series, but you change the weights differently. It has the same problems as what we just showed, that we're assuming stationarity, complete data, global estimates, many parameters. Everything's way overdetermined. We need pseudo inverses, can give funny results, assumes the relationships are linear. And it may just be that we're modeling the seasonal, there really is no information behind that. Okay. So here, whoops, can we go back? Yeah, here we're looking at SST and log chlorophyll. And, you know, what I want to focus on, it does suggest that there's some relationship, but it's not as strong as we'd like. I want to look at this modeled pattern and just keep it in mind. I have some that are even more modeled, and come back to just keep that in mind, because we'll come back to that a little later on. Here's another case, SST, whoops. Okay, here's another one. Again, we see that there's this modeled pattern in the phase. That could just because it's noise, or there could be, again, I just want to keep in mind about the patterns and just look at, there's some evidence that in terms of being able to predict the one from the other, that there is a phase shift. That so there's a low level 1 or 2 dimensional process going on that has a phase shift. Okay, so what I really like to be able to do is work with the same idea in the time domain, where I can do allow to have non-stationarity and still have the underlying shift. There was a paper by Runzler that has not been looked at very much. I know one other paper in the literature that referred to it. It was a paper by some of Koopman's students. And what Runzler shows is that given the state space representation of a cycle, a stochastic cycle, that we can shift units to the right by multiplying by these things where eta there is the level of the shift. And the point of this is we can just put this shift in the observation matrix of the state space. And so we have the underlying, we'll say, single component, and then for each of the observed series, we have a shift of that underlying component. So this allows us to have a stochastic cycle that has changing phase and amplitude, but we have a lower dimension version of it that then's phase shifted for the other variables. Okay. So again, if I can give you, if I'll have my email up at the end, if anybody's interested in the reference, I can send that. And here I just took some data that was real close to each other and just set phase, took one of the series seasonal. I looked at each area individually, did a univariate state-space decomposition. And if we look at it and I use the default, the parameters from that one thing and I set what the phase shifts were. And you know, I just ran the Kalman filter once, you know, forward and backwards to get the smooth estimates. And sure enough, this is for SST. Again, we see the same behavior where there's a single component with a phase shift in the data. And this just doesn't mean it fits the data well. It just shows that Runzler's method really does work. Takes the component and shifts it in time. Okay. Okay, now that takes care of time, but we need to take care of space. And I'm saying when taking care of space, we want something that allows for the heterogeneity in the data, but somehow doesn't make the problem too large. I'm interested not in data with 10 or 15 series. I'm interested where we have tens of thousands or even hundreds of thousands of data. The way we're going to do it is what's called discrete process convolutions. And I don't know whether Ricardo is on, but everything I know about discrete process convolutions is from him, including what code I have is half stolen from him. So thank you. The idea of discrete process convolutions, you set up a grid of that's a much less resolution than your actual data is, and you put a process at each of these grid points. So the process might include a trend, an unparametric trend, a seasonal, a stochastic seasonal, a stochastic cycle. It's whatever you want, but you have one at each of the grid points. And then you have a kernel that extends out the processes at the grid points to each of the observational points. Okay, now this happens to be an example here. It's from a paper we actually were able to do multiple grids in one pass. Unfortunately, the details of this is under an NDA, so I can't go, but we looked at roughly 800,000 series daily for 10 years, and it was done on a laptop. When you do this kind of thing, what you end up with kernels that look like this. This is actually from a paper of Ricardo's where he, I think it was scallops, if I remember correctly. If Ricardo is on, he can correct me. And these shows the kernels. These are like 70% of the coverage of the kernels. And we're using anisotropic kernels that allow for the different size in both this axis and that axis, and allow the kernel to be tilted also. So you end up with kernels that look like this. And so given a process at any point, these kernels then spread the process out to each of the data. Okay, when you do so, here's the result from that study. We can form a climatology and look how the different grids are important. We can see that actually, depending on what we looked at, we actually don't necessarily need the finest grids. But I said I'd come back to modeled patterns. Here are modeled patterns. And I mention this because there's things called Turing patterns. And they arise from when there's a single process that spawns two reactive diffusion equations, where one is diffusing and the other inhibits or blocks that diffusion. And they're known to produce such modeled patterns. Now, that doesn't mean that's what's happening here. These could just be due to noise and we're over-interpreting, but something I've been interested in, if I ever get the smarts and the time to do, to look at. Okay, so to go back to this one, so what we're going to be doing here is we're going to assume, for example, let's say we have one underlying seasonal process or cyclic process. If you know anything about doing dynamic factor analysis, there's a lot of literature. One thing I didn't mention, there's like a paper from Lopes, for example, that shows when we do this, that this defines a non-separable covariance matrix, and though it may be done implicitly. And a lot of problems with a lot of methods done for spatiotemporal data is they use methods where you have to have an analytic expression for the covariance matrix, and that's very hard to obtain. So usually the temporal aspects do not allow for rich temporal things, and yet here we're actually doing the same thing, except we're not getting analytic expression, and allows for a much richer temporal thing. So anyway, for the model, what we're going to do is in DFA, you get better results if the analysis in dynamic factor analysis aren't unique. There's orthogonal transformations that will produce the same results. So normally what's done is one area is picked. We assume we have one common seasonal. One area is usually picked to be that one, so it has a weight of 1, and then the other weights are relative to that area. So we're going to do the same thing. We're going to set one process here. Okay, and it's going to have phase 0. It's just like in the other one, phase 0 is free, and that's then going to get lagged to the other parts, and then then the convolution spreads it out over the series. Okay, and a couple of things is so yeah, this just goes, the whole thing is by doing that, we've shown that the phase lag part is just a multiplication times a thing, and the DPC, the discrete process convolution, is just a linear combination of those. So in terms of the original component, that's all linear. So we can put that all into a dynamic factor model. And so what? Why do we care? 2 results. A result by Youngman, Youngbach, and Koopman that shows that there's a transformation of the observation equation, since the observation equation produces the same result for a given set of parameters as the original. But if you work out the dimensions of this, is the size of the state, not the size of the observations. So if our state, for example, has one seasonal component, it's size 11. So this could be size 10,000, but the transformation makes it size 11. The other thing is what's called univariate treatment of multivariate series. Requires a diagonal observation matrix. If not, we can use the Cholesky decomposition to transform the problem. So we replace an observation vector size n, calculating, so we have to do n by n matrix inverse with n univariate calculations. We can combine these in 2 steps. It produces a collapsed model where the observation error covariance matrix is the identity. So what we have gained is we've reduced the size of problems we need to deal with. Okay, but swept under the rug is the transformation can involve some very large matrices. If diagonal error matrix is not assumed, the Cholesky decomposition can be very hard, and the matrix sometimes is not a full rank. The kernel matrix is very large but sparse, so we need to do coding with sparse matrices. And we now, by having a DPC grid, we're increasing the number of parameters. There's no free lunch. And there's a question of size and placement of the DPC grid, and the number of underlying processes and where to put them, and sensitive initial parameters. And since I'm running late, I'll stop there. I can show some initial results if people want to hang on. So there's my email address. Whoops.
Roy, you have plenty of time still. I think you have.
Really, my watch is showing 103. Oh, that's right. I go to 130. I'm sorry.
Yeah.
That's okay. Thanks, Roy. I know that you said there was something at the center happening at 1, but you're good. We have plenty of time.
No, I don't have to be there. I'm fine.
Thanks.
No, I'm not going to that. That was not a problem for me. I wasn't going to it anyway. So anyway, I would like to go back to these because I rushed through these. the univariate treatment and multivariate series, that's usually people refer to Koopman and Durbin, but it actually goes back to a result by a fellow named Bierman in the engineering literature, and he called it rank 1 updates, and it actually dates to about the late 70s, early 80s. It's been a well-known method of doing it, and whoops, and if you whoops. And I'm saying that one of the key steps in the Kalman filter is that there's an error. You calculate the error of the observations, which is an n by n matrix, and you do an inverse of that, and it gets rid of doing that inverse. And even if it's not faster, it allows you need much less memory and allows things to be done on a laptop. And as I said, you can combine the two steps of the collapsing and the Cholesky decomposition into the Cholesky decomposition, the information matrix followed by QR decomposition. And this will produce a collapsed model where the observational error covariance is the identity matrix, which again simplifies your calculations. One thing about doing this is these kinds of steps, if I were one of the cool kids in the machine learning business, I would call this normalization flows, normalizing flows. I actually have a paper from a year ago in the Gaussian process literature that actually rederives these results without any being awareness of the methods already known. Let me get some water. So it really is non-trivial that we recognize that despite having this whole phase lag of the say single underlying process and the kernels and the whole DPC grid, it still boils down to a linear state space model, and we can use these methods for doing the calculations. It's non-trivial. It can start allowing you to handle very large problems. And these results, by the way, on the collapsing is true for general linear state space model, not just for this. Okay, so what we've gained, we've converted a problem with n observations in k states, where n is much bigger than k, to a problem with k observations in k states in a series of k univariate calculations. And as I said, the example I gave earlier, that was from a paper with Ricardo given at the International Bayesian Statistics Association meeting in Sardinia a few years ago. We estimated a model with 10 years of daily data at almost 1 million locations, and it was done on a laptop. Granted, a well-equipped laptop, but still on a laptop. And, okay, but I really learned in trying to code a lot of this. Everyone should be required to at least have the code for their examples. If not, the actual programs allow you to use it. It's because there are a lot of issues that when I give the math, conveniently gets swept under the rug. And I don't feel like sweeping things under the rug. So the collapsing transformation can involve some very large matrices. So you still need the ability to do that. The Cholesky decomposition can take a lot of time, and depending how your model goes, the matrix might not be a full rank, and therefore you have to do something correct for that. That's something that can be real hard. The kernel matrix is large but very sparse, and so we need to code with sparse matrix routines. And the DPC, the bigger the grid we have, the anastrophic kernels that I'm using, that Ricardo and Bruno Sanso developed in a JASA paper, I think it was 1999, have 4 parameters. So the bigger the grid, the more parameters we have. There is no free lunch in using it. There's questions about the size and placement of the DPC grid, how much that affects the results we get. There's a question of the number of underlying processes we use and where to put the zero phase locations and how much that does or not affect the results we get. And I don't have answers to these. These are things I'm slowly trying to work on. Whoops. And my initial things is there's a fair amount of sensitivity to initial parameter values, and that's particular. Certain initial parameter values will produce a matrix, information matrices that are not a full rank and cause problems. I also want to come back. Whoops. Okay, on this, I give this is the transformation that's usually given, but it's actually, the transformation really is not unique. There's a whole family of matrices that can be used. If this one produces a rank efficient estimate, you can look at their paper for what it is, but determining the best transformation to use is an issue. And you can, if you do get a matrix that's not a full rank, you can change to another one, but coding all that, writing out an equation to do that is a lot harder than when you have to code for it. Okay, test problem. This is mainly the test code. So I had 100 series of SST. These are half degree. I picked 9 3x3 DPC grid. I've fit a state space model to each individual location, and the series, we move the trend in the cycle. I put 2 underlying seasonals, not because I think this really needs to, but because turns out coding for 1 is a lot easier than coding for more than 1. So I wanted the code for at least 2 to make sure that I could do it. And that means that's because you have to keep track of where the zero phase locations are, and so that they don't get affected by any of the neighboring ones. They're only affected by themselves. So view this not as something that I'm viewing as necessarily a really, really good use of the model, but just that, quote, the model sort of works and that I could get code to run. I haven't spent as much time on this as I would like. 1, because I've been really unfocused given a lot of what's going on. And 2, I have another job. If some of you don't know, I myself and 4 people run a data service worldwide that has over 100 terabytes available for people, and keeping all that running, particularly when we're not on location, takes up a lot of time. And I'm saying in R0, the first underlying component is zero phase there, and the second one zero phase there. For seasonals, we would have 6 components, just like when you do a trigonometric seasonal, you would have the same variance here. Each frequency is shifted the same. So even though we could shift them differently, that would really over-parameterize it. We shift them all the same. Here are so we got the estimates. Here are estimates of the kernels you get. As you can see, you can get area specific. These are 70% of the coverage, so they overlap more than shown. You can see you can get different shaped things, and you can have some tilt. And so we can get very location specific effect of things, so that we don't have a homogeneous assumption on how the process at a single location behaves here as compared to here. Okay. And sure enough, here we look at that there really is a phase shift in the data. This looks at the shift. We have to look at each different period, but this looks at a period of 12. And we can see there's a definite phase shift, so that 1 or 2 components very nicely model what's going on, and there definitely is a phase shift, though. So if we try to model it without that, we would have problems. Now you could say, why don't I just put a component at each DPC? Well, 1, and maybe we'd implicitly get the phase shift. 1, that makes the problem much, much larger, particularly if we have a fair number of DPC points. And two, that estimate of the phase shift will probably be noisy because we're not forcing a phase shift. We're not regularizing it in any way. And regularization is very, very good. Okay, and here's an example of the estimated series for 2 locations. And we compare it against the univariate fit. And there is some differences, but we should expect some differences. One, we would never expect an underlying component lower dimensional to totally fit. But two, when we do the individual location, oh, I see the questions and I haven't looked at them. Here we're doing some spatial smoothing, which we weren't doing when we do the individual, so we don't expect them to be identical. We expect some of the neighboring effects to pull things down and remove extreme behavior. Okay, so the main thing of this is it does work. This is doing 100 series. All of this stuff I've shown here is done on my laptop. But there's still a lot of questions, a lot of work. This is really just a work in progress. Okay, so that's it. Now I do have questions, and I'm right on time. So
Excellent.
there's one
Thank you
question,
so much,
and I don't see
Roy,
why.
for that. And to the audience, please feel free to either enter a question in the chat and we'll read it out, or if you would prefer to raise your hand, we can unmute you as well. Thank you
One
so
says
much,
prefer
Roy. We're
not to
clapping.
ask on. Is there a way to extract a sparse covariance and precision matrix to use the suite? The answer, John, is essentially oh yeah, and if we have time, people are interested, I have some initial results on salmon.
Hey, Roy, could you read back the full question? Because
yes, he says
audience
the way
can't
to
see it.
extract a sparse covariance or precision matrix to use discrete process convolution as part of a hierarchical model. And the answer is this essentially is a hierarchical model. When you actually write it out, that's exactly what you have. And you can do it even with another step. And not only can you do it that, though I've shown everything in using a frequency analysis, you can put it in a Bayesian context. It's in fact, all Ricardo's work, which he nicely stuck my name on, is on Bayesian context, not on frequency here. So the answer is yes, it very much can be put in a hierarchical model. We have 2-level process here. You can add another level. So does that answer your question, John?
Yeah, thank you.
Yes, so yes, definitely.
This is Jim Thorson, and thanks, Roy, for giving this talk. I think I have to sort through a bunch of this. I guess one comment is it'd be interesting to try to compare notes, and John Best and I and others have been, as maybe have been doing EOF in kind of a spatial GMRF context, and you can kind of partial out, stationary pieces, or covariate effects more easily, and it's got kind of a generic response, not normal, and it's got some regularization on the spatial piece. So it seems like it has sort of overlap and maybe some pros and some cons.
Oh, definitely, Jim. And that's one reason why I've asked you for a lot of your guys' papers. I just don't have time to really do it. Saying I barely get time to work on this because of the data service. And one thing, as I said, one problem I have is I don't like GMFs because I don't think the data, at least the satellite data that I look at, is spatially homogeneous that way in terms of the distance function. I mean,
Yeah,
I
well,
could
no,
be wrong. It may not make much difference. And so it's a gut reaction, not that I have evidence of that.
yeah, well, no, and I mean, I agree with you, and I mean, like John Best, who I think was just asking, is looking at non-stationary models, and Cecilia has been looking at kind of barrier effect models, and we're hoping to deal with some of that. I guess my question is just my own ignorance. I kind of got here 1 minute late, and maybe you explained it, or maybe I just didn't grok it fast enough. But I guess you're doing this in phase space, and you're applying some transformation of the data to put it in phase space. Or you have like a 2-minute kind of reiteration of how that works,
Yeah,
and whether
no,
how
in the
what would
phase
happen
space,
if you did this on the raw data rather than the phase
yeah, no, the
state.
phase space was the first part. That's an old method in the that was used to look at phase delays, and I did that to look at is there some quick, it's a very quick method to use, and it allows you to look at, is there some evidence that there's phase delay? What I'm really looking at here is the state space. If you can see my screen now, can you see the talk?
Yeah, thank you.
I can bring it up full screen. This is the state space representation of a stochastic cycle, and it's essentially, when you do this, and you can do a seasonal as a number of, for example, for a month, you would have 6 components of these. It's essentially the series plus its Hilbert transform, even though you're not doing it that way, it essentially is the same. And it produces a series with changing phase and amplitude. Okay, and then the key thing is, if we come down here, was this from Runzler. And Runzler shows, given the state space representation of series, we can work it out. We work through the math of it, that we can shift that underlying phase component, we just looked at, which can be either a seasonal or a cycle. We can shift it by an amount, eta time units to the right, by multiplying it by factors like that. And therefore, we can put these things into the observation matrix. We have our underlying component, and so we'd have the underlying component, and then these things in the observation matrix will shift each of them by that phase. So it's shifting it in time, but it's shifting it in a phase sense. Is that making sense, Jim?
And is that the process that's being done at each like DPC point? Is that
yes? So what I'm doing is, I have one area that has one DPC point that has the 0 phase process. Then that one is shifted in phase at all the other DPC points. Okay, so now we have a value at each of the DPC points, right? And those values are shifted by whatever the parameter we've estimated says it should be shifted. And then the value of that DPC point is spread out to the observations based on the kernels. So the value of any observation point is a linear combination of the values at the DPC points. And actually only have a few of them, because you limit how far you go. And if you work that out, that's just a convolution. So we have a convolution of these values. So in terms of the underlying series, that still ends up just as a number times the underlying series. Okay, it takes a lot of calculation to get, but it's still just a number times the underlying series. So that allows us to put that number into the observation matrix, and we're back to our state space model. Does that help?
Yeah, I mean, it's cool. I guess my takeaway, and for the group, is just like, I don't know. I mean, in the spatial people here in Seattle, I don't know too many doing like cyclic or kind of phase space, methods like this. And it's just it'd be interesting to see if anybody at SAFs or there's kind of any resources to explore more. And thanks for coming and presenting this and showing that we've got kind of a missing piece.
Yeah, and one thing, I go back, let me pull this up if I can find it. Okay, as I said, one thing that brought this on, remember I've been asked to look at tuna in the Eastern Tropical Pacific, and this is from an old paper, and it suggested that SST propagated along the coast, and that the tuna, or at least the tuna catches, followed behind it with a lag, and it happened at, this was all done in the frequency domain. So it suggested there was a phase shift. So this was done, when I actually did this, the fact we even got this calculated is amazing. It was, I forget whether they had 64K, 128K, and yes, K, not megabytes, K. to do this. Took a lot of tricks. I wanted to update this to, given that we have more capabilities and methodologies have been greatly improved. So that's one reason why I'm interested in phase relationships, because I wanted to see whether there might be similar relationships between the environment and tuna in the Eastern Pacific. And the idea was to start. This was the first step in looking at that problem. Does that get more into the motivation? So in other words, there are a lot of cases where I don't know this is useful, but for the problem that I'm interested in, it's, that's one of the questions I'm looking to see. What I do think is useful is the collapsing and the univariate processing. That can be used, that's a general result on something that can be put in the state space form. And I'm saying you can be one of the cool kids and call it normalizing flows, and now you're a machine learning guy, and I'm cool, rather than just an old fogey.
Thanks, Roy. A reminder to the audience, if on your control panel, you can click the raise hand feature to ask a question, or feel free to type in the chat.
Yeah, and I would emphasize that there's one takeaway from, despite all that's going on in this model, it still is in the class of linear state space models. And linear state space models can be done Bayesian, they can be done however you want. It's I don't have the results here, but I have already. I've been trying to have the code done about 1,000 series using this. And that's because I haven't tightened up the code. One thing I didn't go in is normally you might assume that the error covariance matrix has the same structure as the kernels, so that it'll be sparse, but has that same structure. So it won't be in and of itself diagonal. So that's why the whole thing on the Cholesky decomposition with the QR, followed by the QR decomposition, to collapse it down to a problem with identity matrix for the observational covariance matrix.
Elena, it looks like there's a question from John Best here. John,
I was
you want
just going to
to
ask John if that was a hand raised from before, but thanks, John.
Yeah, thanks. That's a new question. Thanks again, Roy. To get the nice sparsity in your precision covariance matrix, do you have to use some sort of bounded convolution kernel, or is it pretty general?
No, the sparsity, the observation error matrix can be anything you want it to be. It makes sense, however, to have it follow the same pattern as the DPC grid. So basically, I would assume there's a parameter to be estimated the error at each DPC point, and then the same kernel that used on the processes spreads out the error to the observations. So that's sparse, but not diagonal. The diagonal, by doing the Cholesky decomposition followed by the QR, it will be reduced to the identity matrix. Does that answer it?
Yeah, that makes sense. I was wondering, I guess I was just sort of wondering what the functional form of your actual convolution kernel looks like. Squared or is it?
Look up. I think it's 1999. Lemos and Sanso. Is Ricardo on? He was talking about coming on. Look up Lemos and Sanso, 1999, and I think it's 1999 JASA. I was discussing on it, so you could look it under my name.
Okay.
And that gives the form of the, but what I'm doing, by the way, this is not dependent on the particular kernel that I'm using.
Gotcha. Yeah,
Okay.
I guess that was sort of my question.
Yeah. Oh no, it just assumes there's, all it's saying is I have grids, a DPC grid, and there's a kernel that spreads that DPC grid out to the observations. It's only my code depends on that kernel, And I like that kernel because it allows you to, it changes both the horizontal and vertical axis size and allows the kernel to tilt. Okay, so that it really gives you a lot of play on what areas get influenced by a DPC. But again, that actually has 4 parameters in the code item. I'm only estimating 3 because 1 doesn't seem to change it very much. But you lose something by doing that. You have more parameters, right? There's no free lunch. You know, that could lead to over parameterization.
Yeah, that's great. Thanks a lot.
Yeah, but yes, it's not dependent on the particular form of the kernel I'm using.
Okay,
Hey, Roy,
thank you.
can you hear
Any
me?
other- Oh, great.
Just a quick comment. So the kernel does have to have compact support. So it must go. So the function must evaluate to 0 beyond a certain range in order for the resulting matrices to be sparse. But other
That's
than that, it
Ricardo,
can
by the
be.
way, folks.
Yes. Sorry about that. I should have introduced myself. Yeah. So the kernel does have to be compact support.
Ricardo, what year is the paper in JASA?
2009. I'm not that old.
2009. Okay, I lose track of time. 2009, it's Limos and Sanso.
Yep.
And also, do we actually, of the IBSA talk, is the talk available anyplace? One of the issues on that, as I said, that part of that is covered under a non-disclosure agreement. So there's some key details of how we did that very large problem that we can't talk about. But the parts I did show were all part of his talk in Sardinia, which were cleared. So we're not in any trouble for talking about those parts because that was part of his Sardinia talk. Is that available at all, Ricardo?
The slides, yeah, I can make available to anyone interested. Just shoot me an email, please, or to Roy,
So,
and then he'll forward to me.
yeah, and so yeah, so there's slides giving what we did there. That wasn't, you know, with the phase lag. That's just doing the DPC with processes put at each DPC, and with the kernel that I'm using in here. That was developed in the Limos and Sanso paper. And Ricardo, I'm glad you made it. And as I told you, I mean, I repeat again, what I know about DPCs is from working with Ricardo. He was very nice to stick my name on several papers.
All right. Well, thank you so much, everyone, for attending. Thank you, Roy, for the great talk. And with that, we'll close out, but feel free to stick around as Roy has offered to answer additional questions. So thank you.
Yeah, so let me know if there are any questions. Otherwise,
I'm sorry, Roy, accidentally muted you. You can unmute yourself. Yeah, sorry about that.
No problem. All right. Still have 6 people on the call. Any last questions?
Thanks again, Roy.
yeah, you're welcome.
All right.
Anybody?
Doesn't look like it.
Okay, that's fine.
All right. Great. Thank you so much.
You're welcome. Thank you for having me. I really appreciate it. I don't get a chance to work on statistical problems much anymore, and it's gave me a little incentive to make this a little further along than it was.
Cool. Well, I learned a lot, so thanks.
Yeah, it's great having you. Thank you.
And actually thank Jim for actually arranging this.
That's good.
I sicked him on the on Wiener in Biometric Society to give a talk, so this is his revenge.
Well, other Jim Iannelli says thanks, much appreciated.
Yeah, you're welcome. So anyway, so that's it. Oh, yeah, okay, you're welcome. Like I'm saying, I really appreciate the chance to give this. The data service pretty much chews up my time these years.
Yeah, nice to switch it up.
Yeah.
All right, well,
That was great.
appreciate your time and hope you enjoy the rest of your day down in sunny San Diego. We've had rain since.
Actually, I'm in Santa Cruz.
Oh, you are?
Ah,
Nice. Yeah, I guess we can all work from just about anywhere these days.
No, we have a lab in Santa Cruz.
Got it. Cool. So that's where you're based.
Yeah, and my division used to be in Pacific Grove. Ricardo was actually a postdoc there for a while.